Dear students, welcome to the discussion of deleting a value from the B tree. In this session, we are going to see some examples wherein we make the values delete from the B tree and still maintain the rules of the B tree. As we remember, B tree is a data structure, and the deletion of the keys from the B tree involves removing a specific key and its associated value from the tree. And we have to make sure that the properties of the B tree are considered while doing this. B trees are balanced search trees, which are commonly used in databases and file systems to provide efficient insertion and deletion and the search properties. Deleting a value from the B tree can be a bit complex because it is going to need uh, to maintain the balance and ensure that the tree remains valid according to the properties of the B tree. There are several steps required. Okay, first we need to search the key. And if it is from the leaf node, we have to make sure that there is no case of underflow. So we will discuss what is underflow. If it is internal key, we have to make sure that after deleting the key from the internal node, the internal node is readjusted. Okay, and we will see how to readjust that. Okay, now with this, with this insert with this deletion, sometimes the deletion can become recursive. Like in insertion, we saw a node split at the leaf node can cause another node split at the internal node when both of these nodes are full. So a recursive deletion can also happen. Deleting a value from the leaf node can make it, propagate another deletion from the internal leaf adjustments. So the root node adjustments are very important, and we are going to see how to do that. Basically, we have two conditions arising when we try to delete a value. The first condition is to readjust the B tree after deleting a value by using a borrow method, or readjusting the B tree after deleting a value by using a covalence method. Okay. And in some cases where the leaf node is having more than the minimum number of keys, then the value can be simply deleted without even using borrow or covalence. Now, let us understand all these things by using an example given here. Now, when we talk about the B tree construction, what is very important? We have the order of the tree very important, as we have seen in the insertion. While deletion, we have one more factor very important, which is the minimum number of keys. Okay, so let us consider a B tree whose order is 5. Okay, which means there can be maximum 4 values inside each node and minimum of 2 values inside each node. When the node becomes less than 2, it means the node is underflowing and we need to use the covalence method. Okay, and how do we get this minimum keys? We have a formula which is called as divide the order of the P by 2. Okay, and then seal it and then subtract 1 out of it. So 5 divided by 2, 2.5, seal it becomes, 3. 3 minus 1 is 2. So the minimum number of values inside each node should be 2. For example, here at this node, we have 2 values. If I try to delete 6, I have to use a borrow method to handle the underflow. What do we mean by the term underflow? Underflow means the node is falling less than having the minimum number of values. The minimum number of values are 2. If I delete 6, it will be 1. Then it means this node is underflowing. And then I can readjust the tree by using a borrow method. Okay. Now, if I have a maximum number of keys, okay, 4 and for example, I can delete the fourth value without any problem. For example, I have 1, 2, and 3 here. And if I want to delete one, I can just straight away delete it without using borrow or covalence, because after deleting one, I still have the condition that it is having two values. So 2 and 3 are there, two values are there. So I can delete one without any problem. Okay. But the problem comes when I have the exact minimum number of values. Okay. For example, here in this node, if I try to delete 8, this node can underflow. And then I have to use borrow method to adjust it. Okay, or I have to use covalence method. We'll see how to do how to use borrow and when to use borrow, how to use covalence and when to use covalence. Okay, so this is the case. Now let us see when to use borrow approach. Okay, now we have a tree whose root is 4 and 7. 4 is having left child as 1. 4 is having left child as 1. Let me take the pen. Okay. Okay. So, okay. So this is the root. Okay. This is our root. Okay. 4 is having left child, the root is having middle child, and the root is having the right child. Now we try to delete 6. Okay. So 6 is here, right? So we find 6 here. Now when we try to delete, we will come up with the situation where this middle node will underflow. Okay, underflow. What happens in the underflow? There is the short of keys. So minimum is 2, and after deleting it will become 1, which is dangerous. So I have to balance this, right? So balance can be done by borrowing from the left or from the right. Now here in, borrow from here, we have like, here we have, you see how is it going to look now? This is the final version. Okay. So yeah, in the right child, in the right neighbor, okay, we have in the right sibling, we have 3 values, which is more than minimum required. So this neighbor can give us 1 value. Okay, it can give us 1 value, it can give us, 1 or 2 or 3, but we have to make a decision to move which value out of these 3 in this place. So we have to do this adjustment so that remember our properties of the B tree, which says that, K1 should be less than K2 should be less than K3, and then the trees should follow the range condition, wherein the left subtree should be less than the root. Middle tree should be, between the range, and right should be greater than the root. So we decide to delete 6 here, okay, and we decide that, our right sibling can help us by, lending us 1 value from it, because it is having more than minimum values, more than minimum number of required values. It has 3 values, minimum is 2, so it can give us, it is having 1 extra, it can give us 1 value, okay. So how do we do this? Now here, this is the very important thing, wherein we do the adjustment in order to in order to keep up with the properties of the B tree. So what happens? I cannot simply move this 3 here. So now let us delete 6, or 6 is deleted. Okay. Now what happens? If I just move 3 here, there will be a problem. Here it will be 1 and 2, and then the root is 4, and the right child will become greater than root, which is wrong, which is not the property of a B tree. So what we have to do is we are going to, move this 3 in the root, and we are going to bring this 4 here. Now, when we do this, we are, keeping up with the property or the rule of the B tree, which says that the root value, lower limit and the upper limit should, have the middle child falling in the range greater than or equal to the left one, lower limit, or less than or equal to the right one. So 4 and 5. is falling in the range of 3 and 7. Okay. And the left child is always less than the 3. So we have 1 and 2 less than 3, and the right child is greater than the upper value, which is 7. Okay, and 8 and 9 are greater than 7. So here, this is how the tree is readjusted. Okay, this is how the borrowing mechanism works. Okay, did you get? Okay, now there is another. Now let us make some space for understanding the next method, covalence method. Okay. Now the covalence method tells that, okay, when there is an underflow and you do not have any neighbor with extra values to help. So in this case, we have to adjust the tree by shifting the roots and, merging. Covalence is also called as merging. So what we do is, for example, this root, this sibling is having no extra value, like in this case. Okay, nor the left sibling is having extra value. So in this case, we have to merge them. You see the merged values, and the tree is becoming shorter now. Now, how to do this? Let us understand. So, the second method is the covalence method, which is the opposite of the borrow method. Borrow method says that the neighbor nodes or the sibling nodes will have, if they have more than the minimum number of required values, they can give us. So we borrow from them, and we adjust and we apply the rules of B tree, and we adjust the entire tree. But in the covalence, we do not have our neighboring nodes with any extra values required than the minimum number of values inside it. You see, we are trying to delete 4, and our neighbor is having only 2 value, which is the minimum number of keys required. And the right neighbor also have the minimum number of required values, so they cannot give us any value to adjust or balance our deletion. In this case, what are we going to do is we are going to find the value that we want to delete, and then we are going to merge. Now, while merging, it's like this step. While merging, we have to follow these steps of B tree, which says that key 1 should be less than key 2 should be less than key 3, and the left tree should be less than root, right tree should be greater than root. Okay, so these things we have to follow. Okay, so now let's see how to do that. I'm making space. I can, to avoid confusion. Let me take the pen. Okay. Now we have, for example, here 4 to be deleted. So I'm picking up 4 deleted. Now I have 1 and 2 in the left side, 4 here. Okay. And now what I'm going to do is I'm going to bring this 3 down. Okay. And then I am going to shift this 5 inside the left tree. So my new root is 7, and the left child is 1, 2, 3, 5, and the right child is unchanged. Okay. Now, how can I have 4 values in the node? Yes, we can have it because the maximum number of keys is 1 less than the order. So the order is 5. It means I can have 4 values. Now, when I do this, we are abiding by the rules of B tree, wherein the root is greater than left and less than right child. Okay, and all the values in the root leaf node is sorted 1, 2, 3, 5. Okay, so this is how the deletion is performed. Okay, but when we do not do this, readjustment of bringing down 3, bringing down 3 inside my left child, what will be the problem? I will tell you what will be the problem. And when we do not do like this, okay, so it will be like 1, 2, and 5. I'm just, putting this 5 here. Okay, so the root is going to be 3. Okay, the root is going to be 3 and 7. Okay, 3 and 7. This is going to be the right side child, and this 5 will be the middle child. So this 5 is the middle child, and 8 and 9 is our right child. Okay, now if I just keep it like this, okay, first thing is the middle child will underflow because it should be having two values and it is having only one value. So I have to merge it. If I merge it with the right child, here we will fail because 7 is greater than 5. So 5 cannot move into the right. So I have to move it to the left. Now, when I try to move it to the left, I will have 1, 2, and 5. 5 is greater than 3. So 5 cannot become the right child of 3 because 5 is greater than 3. So what do we have to do? Now I have to bring down this 3 here, okay, so that I can have 5 here, and then my root node will have only one value. Yes, for the root node, it is allowed to have minimum of one value. It is not going to be the underflow for the root. Root can have one value, minimum root can have minimum of one value, but the leaf node should have minimum of two values. So we are, following the rule. That's why we have to bring down 3 as the in the left node. And then when it is 1, 2, 3, and 5, and the root is 7, okay, we are following the properties of the B tree and we are deleting it by readjusting. Okay, so yeah, please practice this, by yourself many times. And then, you can solve one example here. I find this, very good video. So I have put the video here. You can follow along and you can use the tool that we have been using for checking our answers there. Okay. So done. Okay, let's check this one otherwise. So, okay. And I will open. Okay. Okay. And we have, okay, just let me share the screen with this new window. So, okay. So first make the B tree is clear, have the maximum order as 5, insert 1, insert 2, insert 3, 1, 2, 3, 4, 5, 6, 7, 9, 3, 4, 5, 6, 7, 8, 9. Okay. So now, here, if we try to delete 9, if I try to delete 9, there will be no problem. 9 will be deleted. Okay, 9 will be deleted. Okay, now if I try to delete 4, okay, this 5 will underflow. And then we need to follow the merging mechanism, which is called as covalence. Okay, let's delete 4. 4 is delete. Oh, sorry, I inserted 4. So I delete 4. No problem because we have 3 values here. One value can be deleted, right? Now, if I delete 4, it will be problem 5 will underflow. So we merged. Okay. So we brought one root inside the left tree and then we have these values. Okay. Now, because my left tree is having more than minimum required values, if I delete a value from the right tree, 7 or 8, one value will be borrowed from the left tree and the root will be adjusted accordingly. So let us try to delete 7 and see. So delete 7. Okay. And then we see the 5. There is a new root now. Okay. Skip back. Okay, this is the back, right? Now I'm trying to delete 7. Okay, so 7 is deleted and the new root 5 is shifted to the root and 6 from the root has been shifted to the right child. Okay, so this is how the deletion is done. Okay, now when we would, okay, one more thing if you notice, sorry, when we develop a tree with this 5, okay, it did not give us the exact picture like this, but however that's okay. But we are just discussing about the borrow mechanism and the covalence mechanism. Borrow, we saw it worked exactly the way how we did. We borrowed from the left child, readjusted the root, and then we shifted to the right child, like here. Like here, we borrowed from the left child, shifted the root, and then transferred this new root to the right child to deal with the underflow. Covalence method also the same one, right? So we merged, right? Whenever the neighboring root, sorry, the neighboring node or the sibling node also doesn't have extra values more than the minimum required, we cannot borrow. So we merge, and we when we are merging, we make sure that the root is adjusted to follow the properties of the B tree. Okay, so that's it for the delete. And you can do example from here and you can play with some more examples by your own. And now let's see. Let's quickly recap the constraints on the B tree. A B tree of order P is going to give you 1, 2, 3, 4 rules. The fourth rule is very easy to understand, that it should have 4 tree pointers, ultimately making 4 children. Okay. For example, P is 4, there can be 4 children nodes. Okay. Now, every node, every internal node of the B tree is going to have the key pointer, key pointer, key pointer, and the tree pointer, which provides the pointer to the left tree, okay, and the middle tree and the right tree. So this P1 is the pointer to the left tree, P2 is the pointer to the middle tree, and PQ is the pointer to the right tree. Okay, the internal nodes are always sorted, wherein the first key is less than the second, and second is less than the third, and so on until we have all the keys. Okay, and for a tree with order of P, there can be P minus 1 keys. Okay, and the left child will be less than the root. Okay, and the right child will be greater than the root. Okay, so we have while insertion and deletion, all these points are to be considered. Okay, so Now let us see the similarity between the search tree and the B tree. The search tree have the field values in each node that will guide us to the next node until we find the data block that we are trying to search. By using the pointer, we make sure that we search only a specific subtree and we eliminate searching the other keys. For example, in this case, if I want to search for 3, I will come and check at root and I will find that 3 is less than 4. I will check only this subtree. I will eliminate. I will not check this 5 and 6, a middle tree and the right tree. Okay, so this is what is being told here. So other subtrees are not checked. Okay, so these are the similarities between the search tree, but the search tree doesn't follow these 4 rules, and that is why their height is always, unbalanced. Because we follow those rules in the B tree is always balanced, even after insertion and the deletion. Okay, so done. Now, we will do the B plus trees. We will do the B plus trees. Okay, and we'll see how they are advanced how they advance over the B trees with some extra, pointers and additional things. We will see their insertions and the deletions in the next video. But just to give you a hint, how the B plus tree looks like is this slide, wherein we have the B tree for the same values and the B plus tree for the same values. Can you spot the difference? Can you spot the difference? Here we have 1, 2, 3 levels. Here we have 1, 2, 3, 4 levels. And then the leaf nodes or the child nodes are connected with each other. So basically, we store the root node in the leaf nodes. So you see all of them are arranged 10, 20, 30, 40, 50, 60, 70, 80, 90, and 100. Whereas here we have 10 here, 20 here, 30 here, 40 here, 50 like this. We will see what are the advantages and the disadvantages of B trees and the B plus trees in the next video. Thank you.